Hi class, this week we're going to be talking about radicals and rational expressions with radicals. So first of all, let's do a quick reminder of some of the rules that we learned from 221 about exponentials, because a lot of those same rules are going to apply here, or rather all of those rules will apply here. So just a quick reminder, if we have two terms that both are raised to some power and we multiply them by each other, if we have the same base here, same x and x, but two different exponentials. This can simply be written as x times n plus 1. If we have a term like x to the n all raised to another power, so for example, if this n was a 2, we could have x squared, and that term could be cubed or squared. That can be simplified as being x to the n times n. So for example, if n was 2 and m was 3, we would have x to the 6th power here. Okay. We have the division of two exponentials, which I prefer to rewrite everything in terms of multiplication, because multiplication is just easier a lot of the times. So the m on the bottom actually becomes a negative value, if we recall that x to the negative m is the same as 1 over x to the m. Okay, which, using our first rule, can be written as x to the n minus m. And finally, we've got the distribution rule. If we've got x to the n times y to the m, something we can't combine, all raised to the k power, that k term actually comes inside and acts individually on each of the terms inside. Okay, so take a second to look at that. Hopefully that all is familiar to you, but just a quick reminder. I wanted to go over that again. Okay, now let's look at roots. That's mostly what we're going to be focusing on in this chapter. So one you should be familiar with is the square root. So we've got the square root of a. The square root is defined as if we multiply the square root of a value times itself, we'll get that answer back. So for example, if a was 5, we'd have the square root of 5 times the square root of 5 is equal to 5. Okay. Maybe one you haven't seen in a while or haven't seen at all is something called the cube root, where we have that something times itself 3 times gives us that answer back. Okay, so for example, the cube root of 5, again, the cube root of 5 times the cube root of 5 times the cube root of 5 would give us 5 back. Okay? This can be a general term. We can have this x to the, or we can have this, the fourth power, the fourth root, the fifth root, the 10th root. So this is our general notation. I'll show you a different notation a little bit later that is more commonly used. You'll see this sort of notation in a lot of algebra classes, but outside of this, most people don't really use this notation too much more. And just because it's kind of easier, these brackets get a little bit bulky in equations, so we tend to prefer something else, but I'll show you that a little bit. But we can have this n root where n of these values times themselves gives us back that a value. So here we have n of these nth root of a values multiplied, giving us back a. Okay, so let's just look at a quick example. What is the cube root of 27? Well, 3 times itself 3 times gives us 27. So the cube root of 27 is 3. So that's our answer, is 3 here. Good. So a lot of the time, it's really tough to find these. Calculators can do them okay, or calculators can do these fine, but for some numbers, it just becomes difficult to find them. So some of them you'll just kind of pick up with time and remember. Okay, I talked about a different notation. Here we have the square root of x. Another way we can write this is actually x to the 1/2 power. So the square root of x is exactly the same thing as x to the 1/2. Okay, and the cube root, turns out, is x to the 1/3, and this goes on in general. X to the nth root would be x to the 1 over n. Okay, so that's our general notation. So let's use this in a more concrete example. the cube root of t to the 18th. So this would be, in general, this is very ugly looking, so we want to clean this up. So we can rewrite this using our cleaner notation. The cube root goes to the 1/3 power. And remembering our rules from the first slide and in previous classes, we can now multiply those terms. So we have 18 over 3, which can be simplified to t to the 6th power. Okay? So that's one way this is applicable. So let's look at the product of roots. If we have something like x to the root of n, the nth root of x times the nth root of y, we can rewrite that as the nth root of x times y. This only works if all of these roots are the same. Okay, you could prove this using those rules from this first slide. It's actually no different than those exponential rules. It just looks a little bit funny here, but just so that you know, these roots do have to be the same. This would not be the case if this was, for example, an m there. So if this is an m, we can't further simplify this. But if both of these have the same root, then we can simplify it like this. Okay, now let's look at the division of, the division of roots. So if we have a term like this nth root of a over b, just the same as with exponentials, because this really is just an exponential, we can split this up into the nth root of a divided by the nth root of b. Why is this useful? Let's look at an example like this where we've got the square root of 25 over 9. 25 over 9 doesn't really simplify, but it's still a little bit ugly. So we always try to get rid of these if we can. Well, we can rewrite this as the square root of 25 over the square root of 9. Both of these should be numbers you know pretty well. Square root of 25 is 5, and the square root of 9 is 3. So our final answer is 5/3. So we've got this thing that, initially wasn't really obvious what it was, and we ended up actually with a nice simple answer like this. Okay? All right, now probably the trickiest section of radicals is adding them. So if we've got something like the square root of 2 plus the square root of 3, this does not equal the square root of 5. This is a mistake that a lot of students will make. The square, you can't add inside the radicals like this. Prove it to yourself if you need to. Get a calculator, pause the video, plug these numbers in and show that they are in fact not equal to each other. Okay? Okay, so if we have an example like this, we've got a 3 times square root of 5 plus 4 square root of 5. Here they both have these extra square root of 5 terms added to them. So we can just add those leading numbers, the 3 and the 4. Okay, so this is kind of like adding values with an x in it. So if we have 3 times x plus 4 times x, that would give us 7x. This is exactly the same thing. Because remember, x just represents a number here. So in this case, we just want to add like values. Okay? Let's look at a trickier case. We've got this root 3 plus square root of 5 minus 4 square root of 3 plus 6 square root of 5. And that simplifies to 7 square root of 5 minus 3 square root of 3. And what we've done here is we've added like radicals. Okay, so we've got this square root of 5 plus 1 square root of 5 plus 6 square root of 5 equals 7 square root of 5. And we've got a 1 square root of 3 minus 4 square root of 3 gives us negative 3 square root of 3. Okay? So in the next video, we'll look at solving equations with these these radicals and a little bit more tricky behavior. So look forward to seeing you in the next video.